Welcome. This is Chapter 3, Video 4, Measures of Variation, Spread or Dispersion. This is the second half of Section 3.2. I'm Mrs. White, and I am looking forward to being your guide today. Here we go. Here's what I'm hoping you'll learn today: how to calculate the population, standard deviation, and variance for group data. You'll watch me do it manually, and then also with the TI-89. I really want you to focus on how to do it with the TI-89 though, because that's how we're going to be doing it the majority of the time. Second, how to calculate the coefficient of variance. Third, we're going to learn Chebyshev's theorem. Chebyshev's theorem is great, partly because it's just fun to say. Chebyshev's theorem. Chebyshev's. Chebyshev's. It's kind of hard to say it without smiling. Chebyshev's. Yeah, see? Can't be done. And then you also learn the empirical rule, very royal rule. So, empirical rule. So, those are our 4 goals. Let's begin. We are going to go back to the example of the net worth of corporations and take a look at how to calculate the standard deviation and the variance for that. Let's take a look at that. You'll remember that the formula for variance is the sum of every point minus the mean squared. So you take the point minus the mean squared, divide it by n minus 1. That is the formula for sample variance. Now, when you get in group means like this, some genius figured out kind of an easier way to do it. Because if I did it this way, I'd have to figure out the midpoint, and then I'd have to figure out the mean first by figuring out all the midpoints, and I had to put the midpoint here, and then figure out the mean, and I'd have to do midpoint minus mean squared twice, because there's 2 of that for that one, and then do it 8 times, and then 15 times, and 7 times, and 10 times, and 3 times, and it'll be a lot of computations to do this by hand. So some genius rock star who's really good with algebra found out that if you FOIL this out and do a bunch of fancy math, that there's a shortcut formula, and I say shortcut because it looks a little messy, but that looks like this. How many total frequency you have, your total sample size, n. So for us it's 45, because we have 45 companies, times the sum of the frequencies, times each midpoint squared. They put a little m here to remind us that that's going to be the midpoint, minus the sum of the frequencies times the midpoint, and then square that whole thing all over n times n minus 1. So you might be thinking, that's messy and huge and crazy, but don't worry, they have a little procedure table that makes it all kind of work out pretty darn well. So let's take a look at how we're actually going to do this by hand. Okay, I'm only going to do this by hand once. I'm not going to ask you to do this by hand on an exam until Chapter 5. And we do it in Chapter 5 because the procedure changed slightly in Chapter 5, makes it a little less daunting. So in Chapter 5, you will be expected to do this process by hand. Right now, I just want you to see how it works and why it works. So here we go. So here I have my data, and the first thing I have to do is find my midpoints. So I'm going to create a third column. I'm going to call this A, this column B, this column C. Kind of crazy it's in the middle, but we're saving space. And this is for my midpoints. And my midpoint, I remember I take lower limit plus lower limit divided by 2. So 10 plus 21 divided by 2, it's going to be 15.5. Then 21 plus 32 divided by 2 is 26.5. Then 32 plus 45 divided by 2 is going to be 37.5. And then 43 plus 54 divided by 2 is going to be 48.5. And then 54 plus 65 divided by 2 is going to be 59.5. And for our last one, the next class would start at 76, so it's 65 plus 76 divided by 2, and it's 70.5. So each one of these now has a midpoint. Now I'm going to add a fourth column. And this column is going to be the frequency times the midpoint. And this is what you do when you're getting the mean, right? When you're getting the mean, you take the frequency times the midpoint, and then you add them all up and divide by the total frequency. That's what we're going to do here. So you get 15.5 times 2. That's 31. 26.5 times 8, and so on. So I get to 12, and then I continue, and I get 37.5 times 15 is 562.5, and I multiply straight across, and I fill up column D. Alright, so there's column D. And my next part of the procedure is I'm going to go ahead and add the sum of column D. So the sum of this times this. That's adding this column up. So 31 plus 212 plus 562.5 plus 339.5 plus 595 plus 211.5, and I get 1,951.5. Now I'm going to add a fifth and final column. This is going to be column E. Excuse me. And E is going to be the frequency times the midpoint squared. Frequency times the midpoint squared. So if I take this midpoint, 15.5, and square it, and then I multiply it by 2, what number do I get? So I'm going to take 15.5 squared and times that by 2. I should get 480.5. Now I'm going to do that over and over again. 26.5 squared. But this time I'm going to times it by 8. And I'm going to get 5,618. 37.5 squared. This time I'm going to times it by 15. 21,093.75. Then I'm going to take 48.5 squared. Times it by 7. And I'm going to get 16,465.75. Each midpoint gets squared. 59.5 gets squared. And then it's multiplied by its frequency. 35,402.5. And then 70.5 gets squared. Times by its frequency of 3. 14,910.75. And then you get to add all of this up. So this is going to be the sum of the frequency times the midpoints squared. Adding all of these up. So I'm going to add up 480.5. This one, so on. All of these get added up. And my sum is going to be 93,971.25. Add it all up. Now remember that Genius who gave us that shortcut formula? It was the sample variance is equal to n times the sum of the frequencies times the midpoints squared minus the sum of the frequency times the midpoints everything squared all over n times n minus 1. We're now going to put that formula to use. We have 45 n's, 45 corporations, so this formula is now going to become 45 times the sum of the frequency times x squared. So that's this number right here, guys. That's why we bother doing it. So that's 93,971.25. So we're going to square that guy. Or not square it, we're going to multiply it by 45. And then we're going to subtract from it 1951.5 whole thing squared get a really large number that we're going to divide by 45 times 44. Make sure you use parentheses around that or it won't work. And you're going to get a variance of 212.3. That's our sample variance. And because we know the root is the standard deviation, yes, the root is the standard deviation. Since we know that to get this sample standard deviation, we have to take the square root of the variance. We take 212.3 square rooted, and we are going to come up with the fine number of 14.5705. Right? And that is our sample standard deviation. So you can see that this is a very long and messy process, and you might be thinking to yourself, oh self, only if we could do this on our calculator. And yourself might answer you, why yes you can. Just watch the next slide of the video. And you feel great joy and love in your heart as you go to the next slide in this video. Okay, so here we roll with our calculator. The first thing we have to do before we can even put into our calculator is we do need to calculate the midpoints. All right, so again, midpoints, that is something we cannot have our calculator do for us. 10 plus 21 divided by 2, 15.5. Now you'll notice that each one of these goes up by 11. Therefore, the midpoints are going to go up by 11. So if you just add, once you figure out the first one, you just add whatever that width is. If you notice that each one of these are going up by 11, the midpoints all have to go up by 11 too. So just add 11 to each one, and you can very quickly write down. Now don't always add 11, add the width. I mean, obviously if the width is 4, you add 4 to each one. If the width is 7, you add 7. In this case, the width is 11, so I'm going to add 11 to each one and come up with this brilliant midpoint. Now, I am going to go to Apps on my calculator, and our great app in the world, Stats List Editor. Yay! And I am going to clear out my list if I need to. Remember, to clear out a list, you go all the way to the top of the list and you hit clear, and then you push the down arrow button and the numbers will erase. And I am going to put the midpoints into list 1 and the frequencies into list 2. So you're going to have list 1 here and list 2 here. Remember, see how these matched, this one in list 2, and your midpoints are in list 1. Then you're going to hit F4 on your calculator and choose, again, one variable, stats. Don't let the fact that you have 2 lists fool you. This is not 2 different variables. We are only talking about the net worth of 45 national corporations. So we're not talking about 2 different things. We're just talking about our midpoints. The frequency is just letting us know how often those midpoints happen. It's part of the same variable. All right, so then you hit one variable, stats. Then put list 1 where the list is. That's where your midpoints go. And the frequency is where we put list 2, because list 2 was our frequency. So where it says frequency, you change that from the number 1, because each one of these midpoints didn't just happen once. They happened as many times as it says it happened in list 2. So this is telling me that 15.5 happened twice, 26.5 happened 8 times, and so on. So list 1 and list 2, and then hit enter for OK. And then you have your sample standard deviation right here, 14.57. Yay! So that's a wee bit easier than what we just did when we did it by hand. Alright, so to recap, let's go ahead and recap what we just learned. See, that's a cap. That's why that's funny. We're going to recap. We just learned how to find the grouped variance and standard deviation. We learned 2 methods, 2 of them. I like to call method 1 the hard method. You did that by hand with 5 columns. It was a 5-column method where you had a lot of squaring and adding and multiplying and square rooting. It was fantastic. Right? You're not going to have to do that very much because you are mostly going to use method 2, which I call easy and fun method. Right? And that requires using your TI-89. 3 steps. 1, find the midpoints. Put midpoints and frequencies in list 1 and list 2. And then hit F4 one variable stats and get your answers. So, super fun method, hard method. Also fun, but hard. So, we're only going to do this a little bit in Chapter 5, and the data is going to work out a little differently because they're going to be whole population distributions, and the sample size is always going to be 100%. So, it will be a little bit different in Chapter 5. For most of the time now, you are going to do this. Find the midpoints by hand, put in list 1 and list 2, and then use one variable stat. Okay, let's move on to the next slide. This slide is about the coefficient of variance. It's denoted means sometimes you'll see in your book as a C, coefficient of variance, CVAR. Not very exciting denotation, but that it is. It has 2 formulas, one for samples and one for populations. Let me show you what those look like. Ta-da! Here are the formulas. For samples, it's the standard deviation divided by your mean, times 100. For populations, it is the standard deviation divided by your mean, times 100. Hey! The formula is the same. The only thing that changes is the symbolic notation, because this is the symbolic notation we use for samples. And this is the symbolic notation that we use for populations. So, standard deviation divided by mean and gives you the coefficient of variance. And what the coefficient of variance really does is it gives you a percent. It's expressed as a percentage that allows you to compare standard deviations of different types of units. So, for example, suppose that the mean number of samples women fitness, the mean number of pages in a women's fitness magazine was 132 pages. So we have a sample with a mean of 132 pages. And from month to month, those vary. The variance was 23. I said variance. This requires standard deviation, so we're going to take that as the square root of 23. Remember, the root is the standard deviation. So they gave me variance. I want to make it into standard deviation. I take the square root. And then they also take a look at how many advertisements are in one of these fitness magazines. So they realize that in the average fitness magazine, they have 182 advertisements with a variance of 62. Again, they gave me variance. I want standard deviation, so I'm going to go square root of 62. So when I plug this into this formula, standard deviation divided by mean, this one is I am going to get a coefficient of variances of 3.6. When I do the advertisement, this mean divided, this standard deviation divided by this mean, I'm going to get an advertisement coefficient of variance of 4.3. Again, that was the square root of 62 divided by 182. Gave me this coefficient of variance. And now I can say, you know what? The amount of advertising varies more than the amount of pages. So you'll see a lot more shift and flux in the advertisement than you do in the number of pages you might have in a magazine. Hence the coefficient of variance. All right, now you are going to learn Chebyshevs. Chebyshevs, super fun to say. Chebyshevs. Awesome. Chebyshevs is essentially a theorem that tells you what proportion of values fall between certain numbers. Suppose you know that the mean of a distribution is 10 and the standard deviation is 2. Then I can guarantee you that 75% of the data, 75% of all the data has to fall between 6 and 14. How can I guarantee that, you might ask? At least 75% of all the data has to be between 6 and 14. Sorry, I forgot the one there. 6 and 14. The reason I know that is a rule that's called Chebyshev's rule. And what it says is, it says the proportion of the data set that will fall between k standard deviations away from the mean, k standard deviations away from the mean, is 1 minus 1 over k squared. So if you'll notice, if 10 is in the middle, and I go 1 standard deviation up at 2, I get to 12. I go 1 down, I get to 8. That's a distance of 2. Right? Now, so I'm between 8 and 12. That's 1 standard deviation away in both directions. It's not 2 standard deviations away. It's 1 standard deviation away in each direction. So 1 this way and 1 this way. What if I put in the number 1 into this formula? I get 0. If I take this 1 minus 1 over 1 squared, I get 0. That doesn't mean that there are 0 points in the data set between 10 and 12. It means I'm not guaranteed any. There could be some, but I could also get very unlucky. For example, my data sets could be bimodal that happen to look like this. Whole bunch, empty spot, whole bunch. And that empty spot could be between 8 and 12. So I get 0% guarantee. But if I were to go one more set up, one more standard deviation, so I do 1, and then I do another one, so I go 2 more over and get to 14. And then I go 2 more over this way, and I get down to 6. Now I have a 2 in there. 1 over 2 squared, which is 1 minus 1/4, which is 3/4, which is 75%. So if I go 2 standard deviation on either side of the mean, I'm guaranteed 75% by Chebyshev's rule. What if I go 3? What if I just get super greedy and say, hey, give me 3? What happens then? Well, I would go 2 more up, all the way up to 16. 2 more down, all the way down to 4. Now I have 1 minus 1 over 3 squared, which is 1 minus 1/9, which is 8/9, which is 88.89%. So if I have something that ranges that many standard deviations, from 4 to 16, 3 standard deviations, I'm guaranteed to get almost 90% of the data, 88.89%. And the more standard deviations away I go, the more data I'm guaranteed to get. I'll never get to 100%, but I'll get pretty darn close. So that is what Chebyshev's rule says. I'm going to do a couple Chebyshev's problems for you, and then we will move on from there. All right, so let's take a look at this first example, prices of home. The mean prices of houses in a certain neighborhood is $50,000, and the standard deviation is $10,000. Find the price range which at least, could be more than that, but at least 75% of the houses will sell. Well, if I have a mean of 50,000 and a standard deviation of 10,000, Chebyshev says if I go 2 standard deviations away from the mean in each direction, I'm going to get 75%. So I am looking for when k is 2, 75%. So now I'm going to take 2 standard deviations away. 50,000 plus 2 standard deviations, so 50,000 plus 2 times 10,000 is equal to 70,000. And then going the other direction, 50,000 minus 10,000 minus 10,000, 2 standard deviations away, minus 2 times 10,000 is 30,000. So I know that at least 75% of houses in my neighborhood are going to sell between $30,000 and $70,000. And I don't need to know anything else about the distribution or how fast houses move or anything. This is mathematically true. regardless of anything else. So this is mathematically true, regardless of anything weird going on with my distribution. So that's a really important thing. Let's try another example. This example says a survey of local companies found that the mean amount of travel for couriers was 25 cents per mile. All right. So this is our mean travel allowance. And the standard deviation for this guy was 2 cents. Using Chebyshev's theorem, find the minimum percentage of data that will fall between 20 cents and 30 cents. Well, let's see. If I put this on a number line, and 25 cents is in the middle, our mean, and I go down 2 cents, 1 standard deviation, I'm at 23. And I go down 2 cents more, I'm at 21. And if I go down 2 cents more, I'm at 19. But this says 20. 20 is right here. So you will notice that I am 2.5 standard deviations away. 1, 2.5 more. Likewise for 30, if I go up 2 cents, I'm at 27. Up 2 cents more, I'm at 29. Up half of 2 cents, I'm at 30 cents. So again, 2.5, this is a little half one. Only going up 1 instead of 2. So I'm at 2.5. Now I could figure that out mathematically by taking either 20 or 30, one of the endpoints, minus the mean, and divide it by the standard deviation. So midpoint, or endpoint, excuse me, minus the mean, divided by the standard deviation, and that would give me 2.5. So I wouldn't have to draw out the picture. I could use this little formula to find out how many standard deviations away from the mean I am for either of these points. And now that is my k. I'm going to plug that into Chevy. I'm 2.5 standard deviations away from the mean. So I'm going to go 1 minus 1 over 2.5 squared. Do that in my calculator on my home screen. 1 minus parentheses 1 divided by parentheses 2.5 squared, close parentheses, close parentheses. So you have your parentheses. 0.84 is my answer. And that means that there are 84% of all the data values of the actual travel values will fall between 20 and 30%. So if you pay your carrier more than 30% or 30 cents per mile, then you'd be paying considerably more than what the average pay rate is. And you would know that 84%, at least 84%, are paying less than you, right? At least. Could be more. Should be a little bit more. But you know that you're guaranteed at least 84% of the people paying their carriers are going to be paying between 20 cents and 30 cents. So that is that information. Now all of this is without knowing anything about the shape of the data. Things get super crazy when you know something about the shape of the data. For example, all right, so suppose you know that your distribution is normal. It looks like a bell shape like this, right? You get more than what you get from Chebyshev's. So let's do a little quick table here, right? If you have Chebyshev's, you don't know anything about the distribution. And you have 1 standard deviation away, you get nothing guaranteed. But if you have a normal distribution, if you know it's normal, the empirical rule says you go 1 standard deviation away, shoot, that's most of your data. You get 68%, just going 1 standard deviation away in each direction. Right? Chevy says if you go 2 standard deviations, you're guaranteed 75%. In a normal curve, you go 2 standard deviations away in both directions, you are guaranteed 95%. Chebyshev's says if you go 3 standard deviations away, you're guaranteed 88.89%. You're feeling like that's pretty good. But in a normal curve, if you go 3 standard deviations away, you are guaranteed 99.7%. This is the empirical rule. The empirical rule says if you go 1 standard deviation away in a normal curve, you are guaranteed 68% of the data will fall within that. 2 standard deviation away, 95% of the data. And 3, 99.7% of the data. That's pretty amazing. So let's take a quick look at how you might use the empirical rule. Okay, let's check this out. So, let's take a look at this problem. Problem 42 from your text. The average full-time faculty member in a post-secondary degree granting institution works an average of 53 hours a week. So we know that their average is 53 hours a week. We assume the standard deviation is 2.8. What percentage of faculty work more than 58.6 hours? In Part A, they say nothing about the distribution, so I have to use Chevyshev's. So if I go, all right, well, that's an endpoint is 58.6 hours. So 58.6 minus my mean, divide by my standard deviation. That's going to tell me how many standard deviations away I am. So 58.6 minus 53. And I'm going to divide that by that 5.6 divided by 2.8. And I get 2. And I know that we have 2 standard deviations away. I use Chevyshev's. 1 minus 1 over 2 squared, 75%. I have at least 75% in the middle between some number down here and 58.6 up here, right? That means that there's no way only 25% of the faculty could be working more than 58.6 hours. That's the most that the faculty could be working. So, at most, 25% of the faculty work more than 58.6 hours a week. Again, I figured that out using Chevyshev's because it didn't tell me anything about the distribution. Alright, let's play this game again, but this time let's look at part B. Right here. It says, assume a bell-shaped distribution. Now we're looking at this. The empirical rule kicks in because now we know it's an assumed bell-shaped. What percentage of the faculty work more than 58.6 hours per week? Well, again, we know that our mean is 53, and our standard deviation is 2.8. And again, we know if we take our endpoint, 58.6, and minus it from 53, and divide by 2.8, we're going to get 2 standard deviations away from the mean. In the empirical rule, if you go 2 standard deviations away from the mean, we know from our little table, someplace you're going to write down in your notes, 2 standard deviations away from the mean is 95%. That means at most, at the absolute most, you can only have 5% over here and over here. At the most. And because you know this baby is symmetric, that means working more than that, you only have 2.5%. So we narrowed our estimate to at most 25% to at most 2.5%. That's pretty impressive. Pretty impressive indeed. So that is how the empirical rule works. It is quite empirical. Alright, so you've learned how to do 4 things today. You've learned how to, on your calculator, which we are only going to do the easy way, on our calculator, found grouped standard deviations and variances. Second, you can find the coefficient of variance. That is just standard deviation divided by mean, written as a percent, coefficient of variance. Third, you've learned Chebyshev's rule. Chebyshev's rule is probably one of the most difficult things that students struggle with in Chapter 3. Don't make it harder than it is. Draw the mean out in the middle. Draw a little number line and count how many standard deviation steps. Each step is one standard deviation. If your step is 3, you're making a stride with the 3, you go 3 over each time. If your standard deviation is 10, go 10 over each time. Standard deviation is 1,000, go 1,000 over each time. But each standard deviation is a step. And all you're doing with Chebyshev's is asking, if I go so many standard deviations in each direction, what percent of the data will fall in those ranges? So take it slow, ask lots of questions if you need to. Right? And then lastly, you learn about the empirical rule. Same idea as Chebyshev's, but just so much cleaner. Just so much cleaner. All you get to know with the empirical rule is one step guarantees you the 68%. 2 steps, now you're at 95%. And 3 steps gets you all the way to 99.7. So that's the empirical rule. Thanks, and I will see you in video number 5.